Software models are evolving at light speed, but the hardware required to run them is colliding with a literal physical wall. In a standard GPU architecture, the logic processors and the model weights, the actual brain of the AI, live in two different places. The weights are stored in separate banks of high bandwidth memory, or HBM. For every AI token generated, the system must fetch necessary weights, dragging data across a physical bridge between memory and processor. Moving trillions of parameters back and forth creates a massive traffic jam, throttling speed and burning enormous electricity. Overcoming that bottleneck currently requires brute force. To host a single modern frontier model, companies string together thousands of high-end GPUs, filling entire data centers with massive, expensive server clusters. This architecture has become a vacuum for both capital and power. Scaling up AI any further requires changing the underlying physics of how these chips are built. To break that memory wall, AMD recently acquired the startup Taalas. Their strategy relies on building model-specific integrated circuits, or MSICs. The core concept is simple but extreme. Instead of storing a model's weights in separate memory banks and constantly fetching them, Taalas physically bakes the weights directly into the chip's wiring. The model is quite literally etched into a mask-ROM layer on the silicon. The digital software is transformed into a permanent physical structure. The AI is no longer running as fluid code. It is carved in stone. Eliminating the memory fetch bottleneck, a single Taalas test chip served a Llama 3 model at 17,000 tokens a second. That is 48 times faster than standard NVIDIA GPUs and 8.5 times faster than Cerebras accelerators. Because the weights are etched directly into the chip, the space efficiency skyrockets. You would only need about 50 of these accelerators to run a massive trillion-parameter model that would typically require thousands of standard GPUs. But etching your software into metal comes with a severe penalty, a total loss of flexibility. Once the chip rolls off the manufacturing line, you are stuck with that exact model. If a developer wants to update the AI or switch to a newer version, they cannot just push a software patch. They have to execute a physical respin of the hardware, designing and printing a new layout for two metal layers of the chip. AMD is trading the ability to quickly update software for the ability to scale output efficiently. It requires absolute certainty in the specific model you choose to deploy. To mitigate that rigidity, AMD is deploying a disaggregated architecture for their rack-scale systems. This diagram shows the division of labor inside the server rack. Standard Instinct GPUs act as the flexible front end, handling the complex prompt processing, while the heavy lifting of high-speed token generation is entirely offloaded to the hardwired Taalas chips. This massive boost in token generation speed opens the door for widespread test time scaling. This is a technique where developers intentionally allow an AI model to think for a longer period of time before responding, heavily reducing hallucinations and improving logic. Because MISICs push the cost per token down to a fraction of a cent, developers can let a model burn 20 times more tokens on internal reasoning without making the end user wait longer for the final answer. This economic shift is highly appealing to hyperscalers and model developers like Meta or OpenAI, who are already heavy buyers of AMD hardware and need cheap, reliable inference at scale. It signals a transition in data centers from relying solely on flexible jack-of-all-trades GPUs to deploying specialized, single-purpose silicon for frequently used AI agents. If a company has a frontier model they trust completely, they can now physically hardwire its logic into the servers. The next leap in artificial intelligence performance relies on acknowledging physical limits and trading the infinite flexibility of software for the raw efficiency of hardwired thought.